The Cartesian coordinate system was developed by René Descartes to help us get a picture of the solutions of equations. In order for us to understand how the coordinate system works, we first need to know what we mean by an ordered pair. Let's take a look at a definition of an ordered pair. An ordered pair is two elements enclosed in parentheses and separated by a comma. The order of the elements is important. I have illustrated for you here an ordered pair. You'll notice we have the two numbers 3 and 7 separated by a comma and enclosed in parentheses. This ordered pair is different from this ordered pair because the order of the elements changes. So notice here the order of the elements is important in an ordered pair. The element on the left, right here, is called the first coordinate, or sometimes we use the word abscissa. The element on the right side, in this case the 7, is called the second coordinate or the ordinate. You'll notice in this ordered pair, 3 is the first coordinate, whereas in this other ordered pair, 7 is the first coordinate. Since these two ordered pairs do not have the same first coordinate, they are not considered to be the same ordered pair. Your ordered pairs can, of course, contain fractions. You might have an ordered pair of numbers where 1/2 is your first coordinate and 3/4 is your second coordinate. You may also have decimals appearing in ordered pairs, 3.4 being your first coordinate here, and perhaps 7.2 being your second coordinate. We use the Cartesian coordinate system to graph these ordered pairs. Let's take a look at the Cartesian coordinate system. The Cartesian coordinate system consists of two real number lines. You'll notice this darkened line right here being one of those number lines, and a second number line, this one, which is perpendicular to the first one. This horizontal number line that we have pictured here is called the x-axis. And this vertical number line that we have here is called the y-axis. We consider this point right here, where our two axes intersect each other, as the origin. I'll write that word over here. The origin represents the 0 point on each of these number lines. Now on this x-axis, since this is the origin, remember origin means beginning place in a sense, we will start here. Numbers to the right of this 0 point will be positive. So from the origin, if I go in this direction, this would represent 1, 2, 3, 4, and 5 on my number line, and so on. From this origin to the left would be our negative numbers, -1, -2, -3, and so on. The first coordinate of your ordered pair is also sometimes called the x-coordinate. So if I use the ordered pair 3, 7, this 3, which is the first coordinate, is also sometimes called the x-coordinate. That gives me the number that I would find on this x-axis. So for this first coordinate, I would go on the x-axis to 1, 2, 3. The second number is called our y-coordinate. And so we're going to need to find out, how do I locate this y-coordinate on our y-axis? Again, from this point right here, which is the 0 point on this other number line, the numbers above will be positive. So going up, I would have a positive 1, 2, 3, 4, and so on. And going down, I would have a -1, -2, -3, and so on. So to locate this ordered pair on our coordinate system, we have already found our positive 3 on the x-axis. We will now locate positive 7 on our y-axis. 1, 2, 3, 4, 5, 6, 7. That's going to put us right up here at the very top. What we will do is, using these two coordinates, we will go until these lines would intersect at this point right here. So we're saying to get to this point, we would go to a positive 3 on the x-axis, and then we will go a positive 7 units up parallel to the y-axis. This point is where the positive 3 on the x-axis and the positive 7 on the y-axis would intersect each other. This point right here, that is the origin, has the coordinates 0, 0. The x-coordinate is 0, as is the y-coordinate. Let's locate some other ordered pairs on this Cartesian coordinate system. Suppose we have -2 as our first or x-coordinate, and we have 3 as our y or second coordinate. We will do the x-coordinate first. Since this x-coordinate is negative, I will go from the origin to the left, -1, -2. That would be that position right there. Notice that my y-coordinate is positive. On the y-axis, up is positive. So I would go up parallel to the y-axis, 1, 2, 3. Notice that this point right here that has coordinates -2, 3 is the point where -2 on the x-axis and +3 on the y-axis would intersect each other if we come out from those points. Let me go ahead and put the coordinates of this point that we located earlier up here also. Let's locate an ordered pair that has a fractional value. Let's suppose that our x-coordinate is 3/2, and perhaps our y-coordinate is a -1/2. Now recall that 3/2 is 1 and 1/2, and that's a positive number for our x-coordinate. So from the origin, I will go in the positive direction 1 and 1/2 of a unit. And then since my y-coordinate is negative, I will go down 1/2 of a unit. That will place me kind of in the center of that little square right there. This point right here corresponds to the coordinates +3/2. I don't know if you can read that or not, and -1/2. What if our x-coordinate is -4 and our y-coordinate is -5? From the origin, doing the x-coordinate first, we'll go to the left. 1, 2, 3. This will be -4. And then since the y-coordinate is negative, we will go down 1, 2, 3, 4, 5. This point right here has coordinates -4, -5. Let's notice something right here while we're looking at these points that we've graphed. Notice that this first point that I graphed, both x and y were positive. If x and y are both positive, we will go to the right on the x-axis, and then we will go up parallel to the y-axis. So we will end up in this quarter section of our Cartesian coordinate system whenever x and y are both positive. This particular section of our coordinate system is called the first quadrant, and we do our quadrants with Roman numerals. So I'm going to put a Roman numeral 1 there for first quadrant here. Of course, the word quadrant has in it that idea of quad or 4. You'll notice that our two axes, when they intersect, kind of divide our coordinate system into 4 parts here. If we move to this section over here, notice that this point right here has a negative x-coordinate and a positive y-coordinate. This will always happen for points in this part of our Cartesian coordinate system, because if x is negative, we will go to the left, and then if y is positive, we will still go up. This quadrant right here, where x is negative and y is positive, is called quadrant 2, and we use a Roman numeral 2 for that. This fourth of our Cartesian coordinate system contains numbers where x is negative, we would go to the left, y is also negative, we would come down, and so that would put us in this third quadrant of our Cartesian coordinate system. And then the last quadrant that we have here is quadrant number 4. And you'll notice in quadrant number 4, to get to these points, the x-coordinate would have to be positive, bringing us to the right, and our y-coordinate would have to be negative, bringing us down into this quadrant. Now there are some points that are not in any of these quadrants. For instance, the point that has coordinates 0, 3. Notice that since your x-coordinate is 0, from this origin you do not move to the right or to the left, either one. You simply stay on 0 for the x-coordinate. Since the y-coordinate is a positive 3, we will move up 1, 2, 3. This point right here has coordinates 0, 3. That point is on the y-axis. So it is on the boundary, if you will, between quadrants 1 and 2, and it is not considered to be a part of either of those two quadrants. What if I have the point negative 4, 0? Let's look at that. Our x-coordinate is negative, so from the origin we would move to the left, 1, 2, 3, 4. Since our y-coordinate is 0, we do not move up or down. This point right here has coordinates negative 4, 0, and you will notice that point is on the x-axis. Therefore, it is not considered to be part of either quadrants 2 or 3. What about a point that would be down here on this negative part of the y-axis, say this point right here? What would be the coordinates of that point? Well, if we start at the origin, notice that we do not move left or right if we want to get to that point. That means that our x-coordinate would be 0. Since we would move down from the origin, our y-coordinate must be negative. Let's count how many places. 1, 2, 3, 4, 5, 6. We would have to go down 6 places to get to that point. So the coordinates of this point are 0, negative 6. A point that would be over here on the positive part of the y-axis would have a positive x-coordinate and would have a 0 y-coordinate. Now that we've seen kind of how the coordinate system is set up and how we can find these points on the coordinate system, we're ready to talk about graphing the solutions to an equation. Now when we look at points on the coordinate system, the point is actually the graph of the ordered pair. But a lot of times we use the word point and ordered pair interchangeably, and we really don't distinguish between those two. Let's look at what we mean by a solution to an equation in two variables. A solution to an equation in two variables is an ordered pair of real numbers with the property that when the x-coordinate is substituted for x and the y-coordinate is substituted for y, we obtain a true statement. Now, let's just take a look at an ordered pair. Suppose I have the ordered pair 2, 5. Is this a solution to this equation right here? Well, if it is, we must be able to substitute 2 for x and 5 for y. If we do that, if I put a 5 in for y, I'm asking myself, is it true that 5 is equal to 3 times x? Well, if x is 2, 3 times 2 would be a 6 minus this 2 right here. Of course, we can see that 5 does not equal 4. So this ordered pair 2, 5 is not a solution for this equation. Now, how do we find solutions? Since our equation is in this nice format right here, we can find solutions by arbitrarily picking values of x and substituting that into the equation, and by having made that choice for x, we will determine the value for y. For instance, let's decide that we're going to choose x equals 1. So our x coordinate is going to be 1. If I substitute a 1 in for x, let's solve for y. If x is 1, 3 times 1 is a 3 here, minus 2. And of course 3 minus 2 gives me a 1. So whenever x is 1, it turns out that y is also 1. So this particular ordered pair is a solution to this equation. Now this is not the only solution. You might have realized that because of the way we're finding these solutions, I can find many solutions. Let's find a second solution here. Let's suppose that we're going to choose x to be 3. So solving for y, if x is a 3, 3 times 3 would be a 9, subtract 2, and 9 subtract 2 gives me 7. So this ordered pair 3, 7 is also a solution. Let's try some negative numbers here. Suppose I choose -1 for x. Let's see what y would be. If x is a -1, 3 times -1 would be a -3. And then subtract 2 would give me -5. So I have this solution -1, -5. What if I wanted to choose x to be 0? I think you can do this in your head. If x is 0, 3 times 0 would be a 0 here. 0 subtract 2 is -2. You can find many, many more solutions to this equation. And if you wanted to, keep in mind that you could choose fractions. Let's do one fraction just to show what that would be. Let's suppose that we choose x to be the fraction 1/3. I think you'll see why I chose that particular fraction. What is 3 times 1/3? That's going to give me a 1, isn't it? And 1 subtract 2 is -1. So whenever x is 1/3, I get y equals -1, don't I? What we're going to do now is to plot or graph these ordered pairs on this Cartesian coordinate system that we see here. So for this first ordered pair, starting at the origin, my x coordinate is 1, which is positive. I'm going to the right. My y coordinate is 1, which is positive, so I'm going to go up. And I'm just going to put a dot for that point 1, 1. Next, we're going to locate this point. The x coordinate is a positive 3, so I will go to the right, 1, 2, 3. And then since y is positive, I will go up 7. 1, 2, 3, 4, 5, 6, 7. This point, x is -1, so I will go to the left 1. Y is -5. Down 1, 2, 3, 4, 5. That's this point right here. The point 0, -2. X is 0, so I do not move to the right or left. Y is -2, so I will go down 2. Let's see if we can approximate where this point would be. If x is 1/3, I can just kind of estimate here about 1/3 of the distance between 0 and 1, and then my y coordinate is -1. Now you might notice that it appears that these points that we have located here all seem to be lying in a straight line, and that's exactly what's happening. I also want to remind you that we did not find all of the solutions yet. We talked about the fact that we could do this process forever, picking different x values and solving for y. We could pick very large numbers for x. For instance, I could pick 100 for x and find a corresponding y value. If x is 100, 3 times 100 is 300. Subtract 2 gives me 298. Now, of course, my graph paper is not big enough to locate this particular point. But what we're going to do is to connect these points that we have located here with a straight line. And I'm going to put a little arrow on each end of that line to indicate that this line would continue. What we're saying is that this line is a picture of the solutions of this equation right here. And that might be one reason that we call this equation a linear equation, because its picture is a line. And what we're saying is that all of the solutions to this equation will be somewhere on this line. And vice versa, if you pick any point on this line, the coordinates of that point will be a solution. Now, of course, some of these points, like these out in here in this square, we could not read exactly what those coordinates are. But I want to notice that right here it appears that we're exactly on that little corner point right there. The x-coordinate of that point is a 2, and the y-coordinate is a 4. Let's see if that is a solution. If x is 2, 3 times 2 is 6, minus 2 gives me 4, so that point is a solution. If we move off of this line, any of the points that are not on this line will not be a solution for this particular equation. One of the things that I hope you've seen in this example is that when we have an equation that contains two variables, our solution will be an ordered pair of numbers, a number for x and a number for y. We'll write that in the order x coordinate first and y coordinate second. If our equation is in a nice format like the one we just looked at, then it's very easy for us to arbitrarily pick some values for x, substitute that into the equation, and find the corresponding value for y. Because of that process, sometimes we call x the independent variable, and we call y the dependent variable, because the value of y depends upon our choice for x. We're going to look at another example now where the equation is not particularly in a nice form to begin with, but we can rewrite that equation. Let's take a look. We are to graph the equation 3x plus 2y equals 8. Now, let's see if I can focus that just a little bit better. When it says to graph the equation, what it really means is to graph the solutions of the equation, but generally we will just use those words, graph the equation. Now, this equation, if you notice, is not kind of in a nice format like that last one was. So what I'm going to do is take this equation over here and solve it for y. So if I start out with the original form, 3x plus 2y equals 8, I can subtract this 3x from both sides of this equation. If I subtract 3x from this side, this is going to go away and leave 2y by itself. If I subtract 3x on this side, I can either write that as 8 subtract 3x like that, or if you prefer, you can write the x term first and write minus 3x or subtract 3x, and then you'll need to put a plus sign on that 8 because the positive sign is just understood to be there. Either of these forms would be a correct way to write this. Sometimes we prefer that for reasons that you'll see in a later section. Once we have done this, to solve for y, we now need to divide by 2. So we're going to divide both sides of this equation by 2. Dividing 2y by 2, our 2's of course cancel out and leave us y. This 2, recall, needs to divide into both of these terms up here. Since 2 does not divide evenly into 3, we're simply going to write the fraction negative 3 halves x, and then plus 8 divided by 2 gives me a 4. Having written the equation in this form, it's going to be easier for us to choose values for x and find corresponding y values. Let's start by choosing x equals 0 because that will be easy to substitute in. If x is 0, any number times 0 is a 0. So this term will be 0 here, and 0 plus 4 will give me a 4. Now, for our next choice, what you may want to do is to notice that since you're multiplying x by a fraction, and that fraction has 2 in the denominator, it would be nice if that denominator would cancel out. And it will if we choose even numbers for x. So I'm going to suggest that for our next choice, we substitute a 2 in for x. Now, if we multiply negative 3 halves times 2, I'm going to write that over 1, and add 4. Recall that the multiplication occurs first. We may cancel these 2's right here. Negative 3 over 1 plus 4 gives me a positive 1 for my corresponding y value. Let's choose positive 4 for x. So we have negative 3/2 times 4 over 1 plus 4. Again, the multiplication occurs first. We will cancel the 2 into the 4. We'll get 1's down here. Negative 3 times 2 is a negative 6 plus 4. This gives me a negative 2 as the solution. Now, I'm going to suggest that we choose a negative number for x. Let's keep it even, however. Let's use negative 2. If I have negative 3/2 times negative 2 over 1 and then plus 4, my 2's will cancel out, but notice I have a negative 1 left up there when I do that. Negative 3 times negative 1 is a positive 3, plus 4 gives me 7. So I have the ordered pair negative 2, 7. Now, if you recall learning that when you have an equation like this, where x and y are in separate terms, and both are to the first power, this is a linear equation. That tells me that my graph will be a line. And so what I'm going to do is to go ahead and plot these points that we found and see if indeed I'm getting a line here. The point 0, 4, x coordinate 0, positive 4, 1, 2, 3, 4. I have the point 2, 1. I will go to the right 2 and then up 1. Positive 4, 1, 2, 3, 4, and then negative 2, so I will go down 2. And I have negative 2, so I'll go to the right 2, and then up 7. 1, 2, 3, 4, 5, 6, 7. These points do appear to be lying in a straight line, don't they? So let's place a ruler there, and we will connect these points. Recall that we're going to put an arrow indicating that these solutions would continue in both directions here. We have looked at two linear equations as examples. I would like to do several examples now where the equation is not linear, but we can use this same technique of just finding lots of ordered pairs for x and y and then plotting these points and seeing if we see a general trend in what this picture will look like. Let's take a look. Graph the equation y equals x squared plus 2. Now, I know this is not a linear equation because my x variable has an exponent of 2, and with linear equations, those exponents must both be 1s. So let's take a look here. Since this is solved for y, we can just arbitrarily choose some numbers for x and substitute in here to see what we're getting. I decided to start with x equals 0 because that will be easy. 0 squared, of course, is 0. 0 plus 2 gives me a 2 for my y value. Let's choose x to be 1. What do you get when you square 1? 1 squared, of course, is 1, and then plus 2 gives me a 3 for my y value. What about x being 2? What is 2 squared? Well, 2 squared is 4, and then plus this 2 here is going to give me a 6. If x is 3, 3 squared is 9, plus 2 is 11. Now, I'm noticing here that my y values have continued to get big, and actually at this point I know that my graph paper here is not big enough to locate this point 3, 11. So what I'm going to do is to change a little bit here and choose some negative values for x to see what we get for those. It's always a good idea to choose some positives and some negatives to make sure that we get the whole picture here. What happens when you square negative 1? Remember that when you square a negative number, the answer is positive. Negative 1 squared is a positive 1, plus 2 gives me a 3. Well, what about x equals negative 2? If you square negative 2, you get a positive 4, plus 2 is 6. What about negative 3? Are you seeing what's happening here? If we square negative 3, we get a positive 9, plus 2, which is giving us a y value of 11 again. Let's plot these points and see what's happening here. 0, 2. X is 0, I will go up 2. 1, 3, so to the right 1 and then up 1, 2, 3. 2, 6, to the right 2, up 1, 2, 3, 4, 5, 6. Of course, I cannot locate that point 3, 11, but it would be up here somewhere, wouldn't it? Let's locate negative 1, 3. To the left 1 and then up 1, 2, 3. Negative 2 and then positive 6, counting up. And of course, again, this negative 3, 11 is too big for my graph, but it would be up here. I want to show you with this ruler that I'm not getting a straight line. Do you see if I line up these 2 points, it misses this solution up here? If I were to line up these 2 points, I would miss this solution here. So these pieces are not lines. What we have here is a curve. From this point, and we're just going to kind of sketch in a smooth curve that goes through these solutions. And then we know that this curve is going to continue going up because the point 3, 11 is going to be up here somewhere. And then on this side, we will kind of curve up through these solutions. You'll notice that as I came up, I put an arrow on each end of that curve saying that these solutions will continue to be way up here. I think you can see that because we're squaring x here, this is always going to be a positive number. And so when we add 2 to that, we will never get any negative answers for y. In fact, we will never get any answers less than 2. So you'll notice that none of our solutions appear below a y value of 2 for this particular equation. You'll learn later that curves that look like this are called parabolas. Graph the equation y equals the square root of x minus 2. Well, again, since this is solved for y, we can pick some values for x here and substitute in, and we'll be fine. Now, I've been starting with x equals 0. Let's take a look at that. If x is 0, my equation says I have y equals the square root of 0 subtract 2. Well, 0 subtract 2 is negative 2. Well, we've learned that a square root of a negative number is an imaginary or complex number that involves I. This coordinate system, recall, has 2 real number lines as its 2 axes. We cannot locate complex numbers on this type of a coordinate system. So this is not a real number. Since we are not getting a real number, we do not use this or consider this to be a real number solution. This is to help us find real number solutions for this equation. So what we're going to need to do here is to be careful that the choice we make for x will give us a number under here that we can do the square root of in the real number system. Now, you might be thinking, well, I can't use anything smaller than 2, and you're correct. Can we use x equals 2? Well, actually, yes, we can. Y equals the square root of 2 subtract 2. 2 subtract 2, of course, is 0. Does 0 have a square root? Well, yes, it does. The square root of 0 is 0. So we may use an x-coordinate of 2, and we get y equals 0 as the corresponding y value there. Now, let's choose x equals 1. If x is 1, we have the square root of 3 minus 2. Of course, 3 minus 2 gives me a 1, and the square root of 1 is 1. So I have the point 3, 1. What if I choose x to be 4? Y equals the square root of 4 minus 2. 4 minus 2 is a 2. Now, the square root of 2 we cannot do exactly, but if we use a calculator, we can find that this is approximately 1.4. Now, what we will do is kind of use that as an approximate value right there to help us locate that point in a little while. But to help us be real accurate, what we may want to do again is to think about our choice for x. what would be another good number for x so that when we subtract 2, we'll have a number that we can do the exact square root of? Are you thinking of 6? 6 subtract 2 is a 4, isn't it? So the square root of 4 gives me a 2. Did you follow that without us writing it down? Let's plot these points and see what's happening. I have the point 2, 0. That would be right here on this x-axis. I have the point 3, 1, 1, 2, 3, 4, and approximately 1.4. So that's not quite up to 1.5. And I have the point 6, 2. 1, 2, 3, 4, 5, 6, 1, 2. Is it obvious to you that these points are not on a straight line? If you line up these two, you're going to miss these over here. We again have a curve here. From this point, we are curving through these solutions. And I'm going to put an arrow here because I noticed that were I to choose larger numbers, for instance, if I chose x to be 11, 11 minus 2 is a 9, and the square root of 9 is a 3. So if I go out here, x equals 11, my y value is going to be up here on 3. I will continue to get these answers up here. Recall that this symbol means the principal or positive square root, so we are not getting any negative answers for our y value, which we should not do. And since we cannot use any numbers less than 2, you'll notice that there's no graph to the left of this 2 point over here, because numbers to the left of 2 would give us a negative number under that square root sign, and we would not have real number solutions. Graph the equation y squared equals 5 minus x. Now this equation is not solved for y. To solve for y, we would have to take a square root, and actually we'd have to take both square roots. I'm going to suggest here doing something a little bit different, however. I noticed that this x variable here has an exponent of 1. So what I'm going to do is to take this equation, y squared equals 5 subtract x, and I'm going to solve for x instead of solving for y. Now I think the way I'm going to do that, let's add x to both sides of this equation. So I will have an x plus y squared is equal to 5. Adding the x got rid of that minus x over there. And then let's subtract the y squared. So x is going to equal either 5 subtract y squared, or if you prefer, you can write x equals minus y squared plus 5. Now, if we're going to put the equation in this form, it will be more convenient for us to choose values of y instead of x, and then find the corresponding x value. So as we write down these ordered pairs, we're going to need to be careful that when we choose a number, and for instance, if we're going to start with 0, I'm putting 0 over here as the y coordinate because I'm going to substitute that 0 in for y. As we do these values, I also want to remind you that order of operations tells us that this square happens to y before this subtract sign or negative sign happens. So you'll want to be sure that you do that in the correct order. Of course, if we put a 0 in for y, 0 squared is 0, and so if we subtract 0 from 5, we still have a 5. So we're going to have this point right here. Let's choose a positive 1 for y. Now, be careful here. Notice that we're going to put down that subtract sign. If y is 1 and we square 1, we get a 1, and then plus 5. Did you follow that? We squared 1 and got 1, and then this negative sign is still there because of that subtract. And of course, negative 1 plus 5 gives me a 4 for my x value. Well, let's choose a 2 for y. Again, remember, you're going to square 2 first. That gives you a 4. Then you're going to do the negative and plus the 5. So what are we going to get here for x? We're going to get a positive 1. Well, let's try 3. We're working out pretty good so far. If y is a 3, we square 3 and get 9, then do the negative and plus 5. Negative 9 plus 5 is a negative 4, isn't it? Let's choose 4 for y. If I square 4, I have 16. the negative, and then plus the 5. Negative 16 plus 5 is a negative 11. Now, that number kind of got outside of what we're going to be able to graph, didn't it? You'll notice that we've been choosing positive numbers for y. Let's choose a few negatives and see what happens. What if we choose y to be negative 1? Again, be careful. If you square the negative 1 first, you get a positive 1, then this negative out in front puts a negative back in front of it, plus 5, so I'm going to get a 4 there. Right? If I choose a negative 2 for y, if I square negative 2, I get 4. The minus sign then happens, and plus 5, so I'm going to get a 1. And if I choose negative 3, if I square negative 3, I get 9. Minus happens in front, and then plus 5, so I have a negative 4 right there. Let's plot these points and see what's happening. I have the point 5, 0. 1, 2, 3, 4, 5. I have the point 4, 1. 1, 2, 3, 4, 1. I have the point 1, 2. I have the point negative 4. 1, 2, 3, 4. 1, 2, 3. And of course, negative 11, 4 would be up here somewhere. Then I have the point 4. 1, 2, 3, 4. Negative 1. I have the point 1, negative 2, and I have the point negative 4, 1, 2, 3, 4, negative 3. Are you beginning to see the picture here? This looks a lot like that graph that we did earlier that was a parabola, except this one seems to be kind of lying on its side, and that's exactly what we have here. This again is that parabola shape, but our parabola is laying this way instead of like this is the way the graph was that we did earlier in this section. This completes the examples that we have for the Cartesian coordinate system. The important thing here is that you are familiar with the Cartesian coordinate system, that you know how to locate or graph ordered pairs of numbers on this Cartesian coordinate system, and then given an equation in two variables, you know how to go through this process of finding ordered pair solutions for that equation, locating these points or graphing these points on a coordinate system, and this results in a picture or a graph of the solutions of these equations. I hope that you have found this lesson to be beneficial. If you are finished with this lesson, I would appreciate it if you would rewind the tape before you turn it back into the math lab. Thank you very much.